On September 30th, 2025, a spacecraft orbiting Mars turned its camera toward empty space. Over 3 days it captured 57 images of a grey smudge against the stars. That smudge had crossed interstellar space for billions of years before reaching our solar system. It arrived at 58 kilometres per second on a path that can never close. Its name is 3I Atlas, and it is already leaving us forever. The analysis of those 57 frames reached the public only 2 days ago. It describes dust unlike anything our own comets have ever produced. So the question driving everything that follows is uncomfortable and still unanswered. Did we learn what this object was, or only how unprepared we were? Subscribe and tell me in the comments where you are watching from tonight. Let us get into it, because the first clue came from Mars. Part 1. The camera that was never built to look up. The instrument aboard China's Tianwen-1 orbiter is called HIRIC, a high-resolution imaging camera. Its light-collecting aperture measures 0.387 meters across. That is a little under 16 inches, smaller than many amateur telescopes in suburban gardens. The camera was designed to photograph the surface of Mars from close orbital range. It was built for a bright subject, a short distance, and a slow relative motion. Every one of those design assumptions was about to be violated at once. The target was faint, distant, and moving at roughly 86 kilometers per second relative to the spacecraft. That works out to about 53 miles every single second of the encounter. In the time it takes to say the word Mars, the object crossed most of England. Hold that number, because it explains why almost nothing else could photograph this thing properly. The Tianwen-1 team began preparing in early September of 2025. They ran trajectory simulations, modelled the expected brightness, and inspected the instrument for readiness. Then they did something that makes flight controllers genuinely nervous during any mission. They slewed an entire spacecraft to track a target it was never designed to follow. They operated the camera outside its stated design parameters for 3 separate observing windows. The team stacked 30-second exposures across those windows between September 30th and October 3rd. 57 usable frames came out of that improvised campaign at the end. The photographs themselves are frankly unimpressive to any casual eye. You are looking at a soft grey blur against a grainy black background. The scientific value was never in the picture, and that surprises most people who see them. The value sat entirely in the angle from which those frames were captured. Let me explain why the angle mattered more than the resolution ever could. Every telescope on Earth views the solar system from essentially one flat vantage point. Hubble and the James Webb Space Telescope share that same limitation in practice. We all sit near the plane of the planets, looking outward along it. Imagine studying a dinner plate while your chin rests on the tabletop beside it. Tianwen-1 was not sitting on that tabletop when the comet passed by. Orbiting Mars, it caught the object from significantly outside the plane of its orbit. That gave researchers a view no Earth-based instrument could physically achieve. 2 viewing angles on the same dust cloud unlock something a single angle cannot. They unlock the size of the individual grains inside that cloud. That single capability is what makes those 57 blurry frames genuinely important. It is also why the paper describing them took 10 months to reach you. Stay with me here, because the mechanism underneath this carries the entire first hour. When a comet warms, its ices convert directly into gas without melting first. That escaping gas drags solid particles off the surface and into surrounding space. Those particles form the fuzzy halo we call the coma, and the tail behind it. Sunlight is not weightless, and that fact turns out to matter enormously here. Photons carry momentum, so striking a dust grain applies a real physical push. The push is gentle, constant, and always directed away from the sun itself. A tiny grain carries almost no mass but presents a large surface area. Sunlight shoves such a grain easily, sweeping it back into a long sweeping tail. A large grain carries far more mass relative to the surface area catching light. Sunlight barely moves it, so the grain lingers near the nucleus that released it. Astronomers describe this balance with a single ratio they call beta. Beta is the strength of the light pressure divided by the sun's gravitational pull. High beta means light wins the contest, and the grain gets swept away. Low beta means gravity wins, and the grain simply drifts nearby for weeks. Picture standing at a windy bus stop holding two objects in your hands. In one hand you hold a sheet of paper, in the other a house brick. The same wind strikes both objects with exactly the same force per area. The paper vanishes instantly while the brick does not shift a millimetre. Sunlight is that wind, and cometary dust sits somewhere between paper and brick. The whole scientific game is working out where on that spectrum it sits. Remember the paper and the brick, because both return several times tonight. The Tianwen-1 team compared their frames against established dust dynamical models. The beta values came back between 1,000th and 100th of the scale. That range is low, and in cometary terms it is remarkably low. Working backwards from beta gives you the physical size of the grains involved. The answer landed at a few hundred microns across for the dominant population. A single human hair measures roughly 70 microns in thickness for comparison, so these particles run several times wider than the hair on your head. That sounds microscopic, and individually it is entirely invisible to the naked eye. In cometary terms, however, those grains are enormous and genuinely unusual. This comet was not throwing smoke into space around itself. It was throwing something much closer to coarse sand or fine gravel. The grains were leaving the surface at 3 to 10 meters per second. That is roughly the speed of a person jogging along a pavement. The paper describing all of this comes from Xin Ren and colleagues. They work at the National Astronomical Observatories of the Chinese Academy of Sciences. Their results appeared in the Astrophysical Journal Letters, volume 1003. The preprint went up in March, and formal publication followed on May 14th. The wider public encountered these findings only in the past several days. Buried inside that paper sits one sentence that reframes the entire object. The authors note that both properly examined interstellar comets share this large grain dominance. 2I Borisov showed it in 2019, and 3I Atlas showed it again. Both objects also carry unusually high quantities of what chemists call supervolatiles. Their stated conclusion is that these bodies formed in the outer regions of their parent disks. Read that phrase again, because the possessive pronoun is doing enormous work. Not our disk, and not our sun, but their disk around some other star. Whatever system produced this object, it assembled far out on that system's frozen edge. Nothing there ever warmed enough to process fine material into the mixture. That is a genuine measurement about a planetary system we will never visit. It was extracted from 57 blurry frames taken by an improvising team. And nobody on Earth can now check that measurement against a fresh observation. The object sits roughly 1 billion kilometres away tonight, fading past magnitude 15. Every telescope capable of resolving it is losing the ability week by week. There is one more reason those 57 frames carried such weight. During the days surrounding that encounter, Earth-based options were already narrowing. The object was approaching the region of sky nearest the Sun. Ground telescopes were losing it into twilight week by week. Mars, meanwhile, sat in a completely different part of its orbit. From that vantage, the comet remained comfortably observable against dark sky. The same geometry that blinded us gave Mars a clear view. Nobody planned that arrangement, and nobody could have arranged it deliberately. So the finding stands, unverified and unverifiable, for as long as our species lasts. To understand how we ended up in that position, we need to go backwards. The story starts on a night in Chile, when a computer flagged something ordinary. Part 2, the night the orbit refused to close. July 1st, 2025, at a telescope in Rio Hurtado, in northern Chile. The facility belongs to a NASA-funded survey network called ATLAS. Those letters stand for the Asteroid Terrestrial Impact Last Alert System. The system exists to find rocks, that might one day strike this planet. Its software flagged a moving point of light and assigned it a temporary label. That label was A11PL3Z, a filing code rather than a name. Larry Deno is a senior software engineer and co-principal investigator on Atlas. He works at the University of Hawaii's Institute for Astronomy in Honolulu. Deno watched the detection emerge from the automated pipeline that morning. His own description of the moment is refreshingly free of drama or hindsight. He thought it was, in his words, a completely garden variety new near-Earth object. That reaction was entirely reasonable, because such objects turn up constantly in survey data. Then the orbit fits started coming back wrong, and they kept coming back wrong. I want to explain what that phrase means, because everything hinges on it. When you detect a moving object, you record its position across multiple nights. Software then fits an orbital path through those recorded positions in 3 dimensions. Follow this next distinction closely, because everything else depends upon it. Every object gravitationally bound to our Sun follows a closed path called an ellipse. It travels around, and eventually it returns to where it started. Astronomers describe how stretched that ellipse is using a value called eccentricity. A perfect circle has an eccentricity of exactly 0 on that scale. A stretched oval might sit at 0.6, or perhaps 0.9. Halley's Comet is about as stretched as ordinary solar system objects ever get. Its eccentricity sits at roughly 0.967, and it still returns. The critical threshold in all of this sits at exactly 1.0. Below 1, the path closes and the object comes back around eventually. At exactly 1, the path is parabolic and balanced on a knife edge. Above 1, the path becomes hyperbolic, and hyperbolic paths never close at all. Such an object arrives once, swings around the Sun, and departs permanently. The Atlas software kept trying to fit a closed orbit to this detection. Every attempt came back poor, and Deno noticed the pattern quickly. His account is that the trajectory said the object was moving genuinely fast. It said, in his phrasing, that the thing was not bound to the Sun. Darryl Seligman is an astronomer at Michigan State University who studies these objects. He woke around 1 in the morning to find his inbox already full. Marco Michelli at the European Space Agency had written to him overnight. So had Davide Farnocchia at NASA's Jet Propulsion Laboratory in California. Both were telling Seligman the same thing, which was that this looked real. Seligman later described waking to those messages as the moment everything changed. Now watch how professional caution actually operates under genuine pressure. Deno's public statement afterward was measured rather than triumphant in any way. He said they had experienced false alarms about interesting objects before. They knew, he explained, not to get too excited on the first day, but the incoming observations were all consistent with one another that night. Late that evening, he said, it looked like they had the real thing. That is what genuine expertise sounds like when the stakes are high. Not certainty, but judgment withheld until the measurements force a conclusion. And on this occasion the measurements forced the conclusion very quickly indeed. The final eccentricity value for 3i Atlas is approximately 6.14. I need you to feel the weight of that number properly. Halley's Comet sits at 0.967, and it returns every 76 years. Comets arriving from the distant Oort cloud sometimes reach 1.001. Occasionally they reach 1.005 after a gravitational nudge. Those objects barely cross the threshold, usually because a passing star disturbed them. 6.14 does not barely cross anything at all. It is the most extreme value ever recorded for any object crossing our system. A team led by De La Fuente Marcos calculated the statistical significance directly. They put the confidence in the hyperbolic orbit above 1,700 sigma. In experimental particle physics, 5 sigma is the standard for announcing a discovery. 1,700 sigma is not a result that leaves room for argument. Their published conclusion states the position with unusual bluntness for a journal. No known process, they wrote, can explain such an eccentricity from local origins. That includes close encounters with every known planet in our solar system. An extrasolar origin, they concluded, emerges as the single remaining alternative. Let me give you a sense of what Atlas actually does daily. The network operates telescopes in Hawaii, Chile, and South Africa. Each one scans large areas of sky several times per night. Software compares each image against previous images of the same field. Anything that moves between exposures gets flagged for human review. The system finds thousands of moving objects every single year. The overwhelming majority are ordinary asteroids on ordinary bound orbits. A handful each year approach closely enough to warrant genuine attention. Atlas has provided advance warning of several small impactors before entry. Its entire design philosophy assumes objects belonging to our own system. Nothing in the software architecture anticipated a genuinely hyperbolic intruder. When the orbit solver failed repeatedly, it was working exactly as designed. It simply had no category available for what it was seeing. That detail deserves rather more weight than it usually receives. Our detection infrastructure was built around a specific assumption about physics. The assumption was that everything we find belongs here permanently. 3i Atlas broke that assumption within hours of its detection. There was no debate to be had, and there never really was one. The object had come from somewhere else, and the mathematics simply confirmed it. But confirming where it came from raised a far more awkward question immediately. If it was already here in July, how long had it been approaching unseen? Part 3. The 55 days it sat in our data unnoticed. Once astronomers knew what to look for, they went hunting through the archives. What they found made the discovery story considerably stranger than it first appeared. NASA's TESS spacecraft is a planet hunting telescope that stares at large sky regions. It had been observing that patch almost continuously from May 7th onward. Its coverage ran until June 2nd of 2025 without significant interruption. 3i Atlas was sitting inside that dataset for the entire period. 55 days passed before any human being discovered the object independently. Nobody had noticed it, because nobody had any reason to look there. The Zwicky Transient Facility at Palomar had captured it from May 22nd. The Vera Rubin Observatory recorded it during science verification on June 21st. Rubin had not even formally begun survey operations at that point. An amateur astronomer named Sam Dean searched the Atlas archive himself afterward. He found detections from early June that the automated pipeline had passed over. Mark that detail, because amateur astronomers recur throughout this entire story. So the object had been photographed repeatedly before anyone recognized what it was. The reason it escaped notice for so long is almost poetic in retrospect. It approached against the galactic center, the most crowded region of our sky. That direction contains the densest concentration of background stars visible from Earth. Deno made a specific point of this in his comments afterward. He said finding it toward the galactic center was especially gratifying professionally. That region is a challenging place to survey because of all those background stars. Most other surveys, he noted, simply do not look in that direction. An object from another star system approached us hidden behind 100 billion others. By the time anyone saw it, the thing had been active for weeks. Dust was already streaming off it at 6.4 astronomical units. 1 astronomical unit is the distance between the Earth and the Sun. So 6.4 astronomical units places it well beyond Jupiter's orbit. Something was already boiling off that surface out in the deep cold. I want you to hold on to that fact, because it becomes important later. Normal comets from our own system do very little at that distance. Now let me be precise about the timeline that resulted from this discovery. First detection came on July 1st, 2025 at Rho Hurtado. Perihelion, the closest approach to the Sun, arrived on October 29th. That gives a window of 120 days between those two dates. That gave the human species precisely 4 months of available study time. 4 months to study the third interstellar object in recorded history. 4 months to decide what to do, propose it, build it, and launch it. Compare that against how planetary missions normally operate in the real world. NASA's Europa Clipper spent roughly a decade in development before its launch. The Rosetta mission that orbited Comet 67P took over 10 years. ESA proposed Rosetta in the 1980s, and it reached its target in 2014. Development timelines for interplanetary spacecraft are measured in decades, not seasons. Against that institutional reality, 120 days is functionally zero, and the clock had already been running for 55 days before anyone noticed. That is the structural problem sitting underneath everything else in this story. Detection came late, because detection always comes late for objects like this. These bodies are dark, small, and travelling faster than anything we track routinely. They become visible only when sunlight reaches them at close enough range. By then, they are already inside the solar system and already leaving. I want to explain precisely why detection always arrives late here. An object like this is dark, and it produces no light. We see it only by sunlight reflecting off its surface. That reflected brightness falls away with increasing distance extremely rapidly. The relationship involves the distance to the sun and to us. Combined, those factors mean brightness drops roughly as the fourth power. Double the distance, and the object appears roughly 16 times fainter. Triple the distance, and it appears about 80 times fainter. So an object becomes visible only when it is already close. By the time sunlight makes it bright enough to detect, it has arrived. And an interstellar object arrives moving far faster than local asteroids. Consider what that combination actually means in practical observing terms. An ordinary near-Earth asteroid moves at perhaps 15 kilometres per second. We can track it across multiple oppositions spanning several years. Its orbit is closed, so it returns and can be observed again. An interstellar object grants none of those advantages to anyone. It brightens, it passes, and it fades, all within months. Every observation must be made during that single narrow window. There is no second apparition and no opportunity to try again. Let me put the 4-month window against something more familiar. Consider how long it takes to build any spacecraft instrument. A camera destined for deep space undergoes years of qualification testing. It must survive vibration, vacuum, radiation, and extreme temperature cycling. Flight software alone typically requires 2 to 3 years of development. Every line gets reviewed, tested, and reviewed again by separate teams. A single uncorrected error can end a mission worth hundreds of millions. That caution is entirely justified by the history of spaceflight. Then comes integration, where instruments are mounted onto the spacecraft bus. Then, environmental testing of the assembled vehicle, which takes many months. Then shipping to the launch site, and final preparation there. Launch windows themselves open only when the planets align appropriately. None of that compresses into 120 days. No amount of urgency changes the physics of qualification testing. No budget increase makes a vibration test campaign finish any sooner. Which is precisely why the only viable answer was something already built. It had to be already fueled, already tested, and already positioned. The window did not require us to build anything at all. It required us to have built something earlier, without knowing why. So the discovery was not a triumph, whatever the press releases suggested at the time. It was a warning delivered 55 days late about a deadline we could not meet, and the geometry of the encounter was about to make that problem considerably worse. Part 4. The visitor that came in against the traffic. Let me walk through the geometry, because geometry determined every decision that followed, not funding and not politics, but the physical arrangement of the encounter. 3I Atlas arrived on what astronomers describe as a retrograde path. Its orbital inclination measures roughly 175 degrees. Picture our solar system as a spinning vinyl record on a turntable. All 8 planets orbit in the same direction, roughly within one flat plane. Inclination of 0 degrees means travelling within that plane, matching everyone else. Inclination of 180 degrees means travelling in the exact opposite direction. 175 degrees means this object came in almost directly against traffic. It sat less than 5 degrees off the plane of the planets. That arrangement carries a specific and unforgiving physical consequence for anyone chasing it. When 2 objects move in opposite directions, relative speed becomes the sum of both. This is why a head-on collision is so much worse than a rear-end impact. The closing speeds add together rather than partially cancelling one another out. 3i Atlas was not merely fast in absolute terms across our system, it was fast in the single worst possible direction for interception. At its closest approach to the Sun, it moved at 68.3 kilometres per second. Far from the Sun, it travels at roughly 58 kilometres per second. That second figure is its arrival speed and its eventual departure speed. Carry that number forward, because it becomes the most consequential figure tonight. Perihelion occurred on October 29th, 2025, at 1.356 astronomical units. That distance places it inside the orbit of Mars, but well outside Earth's. So the object dipped into the inner system without approaching our planet closely. Let me be completely clear about the danger, because enormous nonsense circulated online. 3i Atlas never posed any threat whatsoever to this planet. Not a small threat, not a monitored threat, and not a theoretical one. NASA's official wording stated that it posed no threat to Earth. The agency added that it would come no closer than 170 million miles. That closest approach happened on December 19th, 2025, at 1.8 astronomical units. In metric terms, that means about 270 million kilometres of separation. For scale, that distance exceeds 700 times the gap to our moon. Now hold that reassurance loosely, because it conceals a much larger problem. This object was harmless, and that was never seriously in question. The uncomfortable part is what it demonstrated about objects that are not. Consider what happened on February 15th, 2013 above Russia. A body roughly 20 meters across entered the atmosphere over Chelyabinsk. It exploded with the energy of about 30 Hiroshima bombs combined. Roughly 1,500 people were injured across that city. Almost every one of those injuries came from flying window glass. People heard the sound and walked to their windows to look outside. The shockwave arrived afterward and blew the glass inward at them. Nobody saw that object coming, not for a single minute beforehand. Our telescopes were not weak, and our surveys were not idle. The object approached from the direction of the Sun itself. That is the one direction no ground-based telescope can ever observe. Sunlight simply overwhelms anything at all approaching from behind it. Now consider the larger historical case that specialists cite constantly. On June 30th, 1908, something exploded above Siberia. The Tunguska event flattened roughly 2,000 square kilometres of forest. Estimates suggest around 80 million trees were knocked flat that day. That object measured somewhere between 50 and 60 metres across. Had it arrived 4 hours later, a city would have rotated beneath it. Nobody detected it, because in 1908 nobody was looking anywhere. I raise both cases tonight for one specific and uncomfortable reason. Meaningful survey capability is younger than most people watching this, and 3i Atlas arrived far faster than either of those objects did. It moved at 58 kilometres per second rather than the usual 20. Imagine an interstellar object ever arriving on an actual collision course. The warning time would be months rather than the years we assume. The closing speed would be roughly triple that of an ordinary asteroid. Every deflection technique we have developed assumes neither of those conditions, so the safety of this particular visitor is genuinely reassuring news. What it revealed about the general case is considerably less so, and here is where the reassurance stops being the interesting part of the story. Because the object we were never in danger from was still leaving permanently, every question we failed to answer during those 4 months became unanswerable afterward. The safety was never in doubt, and the loss was never avoidable. Watch what the same geometry did for one of our neighbouring planets. On October 3rd, 2025, the object passed Mars at close range. The separation measured 0.195 astronomical units at closest approach. That works out to roughly 29 million kilometres between comet and planet. By interplanetary standards, that counts as an extremely close encounter. Every functioning spacecraft orbiting Mars had a better view than anything near Earth. One rover standing on the Martian surface also had a better view. That single accident of orbital timing shaped everything we now know. Then, on March 16th of this year, the object passed Jupiter. The closest approach measured roughly 3.56 million kilometres from that planet. I want you to hold that Jupiter figure carefully in mind. Somebody is going to build a very large argument upon it later. You should hear the raw measurement before you encounter anyone's interpretation of it. There is one more consequence of the geometry that nobody anticipated properly. During perihelion, the object sat almost directly behind the Sun from our viewpoint. Astronomers call that arrangement solar conjunction, and it blinds every Earth-based telescope. The most scientifically valuable weeks of the entire encounter happened behind a curtain. We will return to those weeks, because they nearly cost us everything. But first there is a simpler question that still has no confident answer. How large was this object that passed through our solar system? Part 5. The thing we photographed constantly and never once measured. I have to be honest with you, and honesty here is less satisfying than confidence. We do not know how big 3I Atlas actually was. We never established it, and we are never going to establish it now. The earliest estimates from July 2025 ran as high as 20 kilometres across. The European Space Agency's first public statement described it in those terms. It was thought to be up to 20 kilometres wide, the agency said. That figure circulated widely across news coverage for several weeks afterward. It was wrong, or at minimum it was badly overstated, and the reason instructs us. When you photograph an active comet, you do not photograph the solid body. You photograph the cloud of gas and dust surrounding that solid body. The cloud is thousands of times larger and vastly brighter than the nucleus inside. Think about a person standing inside a dense cloud of steam. You can see the steam clearly from a considerable distance away. You cannot see the person, and you cannot estimate their height from the steam. Estimating a comet nucleus from its coma poses exactly that problem. Remember that figure in the steam, because we return to them later tonight. Hubble observations by David Jewett and Jane Lua-Ookla narrowed the range considerably. Their constraint placed the nucleus between roughly 440 metres and 5.6 kilometres. That remains the most rigorous published bracket on the object's physical size. Later work after perihelion pushed toward the smaller end of that range. Modelling based on how much outgassing altered the object's path suggested smaller figures. That analysis indicated a nucleus between 300 and 750 metres. Other post-perihelion work suggested something between 1 and 2.5 kilometres. At NASA's briefing in November 2025, Tom Statler addressed the question directly. Statler serves as the agency's lead scientist for solar system small bodies. He described the range as anywhere from a couple of thousand feet to a couple of miles. That is an honest answer, and it is also a deeply unsatisfying one. So the position tonight, in late July 2026, is genuinely uncomfortable. The third interstellar object ever observed might be 400 metres wide. It might equally be 5 kilometres wide, and both remain consistent with our data. We never resolved it into a disk, and no instrument ever will. Let me put that uncertainty into terms you can actually picture. That range spans a factor of more than 10 in linear dimension. In volume, which is what actually matters for mass, the range spans over 1,000. Imagine being told an object is between a city block and a small mountain. Now imagine being told the measuring window has permanently closed. That is precisely where we sit with this particular question tonight. The circulating mass estimate rests entirely on assumptions rather than direct measurement. It assumes a density, and it assumes a size within that enormous range. You might reasonably ask why the size matters as much as it does. Size determines mass, and mass then determines almost everything else. It determines how much material the object could deliver anywhere. It determines the energy involved in any hypothetical collision anywhere. It also determines how the object responds to its own outgassing. A small nucleus venting gas gets pushed measurably off course. A large nucleus venting identically barely registers the same force. So the non-gravitational acceleration we measured depends entirely on unknown mass. That creates a genuinely circular problem for the orbital modelers. To calculate the mass, you need to know the acceleration precisely. To interpret the acceleration, you need to know the mass already. Researchers break that circle by assuming values and testing consequences. Those assumptions are reasonable, and they remain assumptions all the same. Every published figure downstream of the nucleus size inherits that uncertainty. The mass, the density, and the total material budget all remain approximate. Now consider what a spacecraft flyby would have delivered instead. A single close pass would have resolved the nucleus directly. One image from a few thousand kilometres settles the question permanently. Every derived quantity would have collapsed from a range to a number. Notice what just happened across that whole sequence of careful measurements. Each new instrument narrowed the uncertainty without ever eliminating it. Then the object receded, and the narrowing simply stopped where it stood. That pattern repeats across every open question in this story. The answers did not turn out wrong, which would at least be correctable. Compare that situation against how we handled a comet in our own system. The Rosetta mission reached Comet 67P in 2014. It did not fly past that object at high speed. It entered orbit around it and stayed for 2 full years. Rosetta watched the comet approach the Sun and become active. It measured the changing composition across an entire perihelion passage. It deployed a lander onto the surface itself in November 2014. The mission returned results that are still being analysed today. That is what studying a comet properly actually looks like. Years of observation, from close range, with instruments designed for the task. Every surprising measurement could be checked against another instrument immediately. Every ambiguity could be resolved by looking again the following week. Now hold Rosetta beside what we managed with 3i Atlas. 57 frames from a borrowed camera at 29 million kilometres. We managed a handful of spectra squeezed between other scheduled observations. We gathered position measurements from spacecraft doing entirely different jobs. The gap between those two situations is not about competence. Rosetta took over a decade to plan and a decade to fly. The comet it visited had been known and tracked for many years. We knew exactly where that comet would be and precisely when. The answers stopped being obtainable, which is a fundamentally different problem. A wrong measurement invites a better measurement from somebody else. An unobtainable measurement invites nothing at all from anyone, ever again. And yet, despite never measuring its size, we learned its chemistry in detail. That contradiction sits at the heart of what happened over the following months. Because while the nucleus stayed hidden, the material leaving it did not. Everything that escaped that surface passed through instruments across 2 planets. And what those instruments found matched nothing in our own solar system. Part 6. The engine that runs on cold instead of fire. I want to slow down and explain the machine at the centre of this. Understand this process and you will understand every comet you ever see. There is no fire involved anywhere in a comet, at any point. Nothing burns, and no combustion of any kind occurs on that surface. What happens instead is a process that physicists call sublimation. On Earth, ice melts into water and water evaporates into vapour. That middle step requires atmospheric pressure holding the liquid together. In a vacuum, there is no pressure to maintain a liquid state, so ice skips the liquid stage entirely and becomes gas directly. You have seen this if you have ever handled dry ice at close range. Frozen carbon dioxide fumes away into vapour without ever forming a puddle. A comet nucleus is a loose aggregate of ice, dust and rock. Out in deep space, the aggregate stays completely inert for billions of years. Then it falls toward a star, and sunlight starts depositing energy into the surface. The ices begin converting directly into gas across the sunlit face. That gas expands outward in every direction with nothing to stop it. The expanding cloud forms a roughly spherical halo we call the coma. As the gas rushes outward, it drags dust grains along with it. Solid material lifts off the surface and joins the expanding cloud. That is the entire engine, and it runs purely on sunlight and cold. The scale of the resulting structure is genuinely difficult to hold in mind. The Aspheric Space Telescope detected an extended carbon dioxide coma around this object. It measured something like 348,000 kilometres across. That is nearly the distance between the Earth and our moon. Let me say that again, because the proportions barely seem credible. A body possibly smaller than a kilometre wore a cloud spanning the Earth-Moon gap. Imagine a marble sitting at the centre of a cathedral filled with mist. The mist is the only part any observer can actually see. The marble stays hidden regardless of how good your instruments happen to be. That marble in the cathedral explains our size problem from the previous part. It also explains why every early estimate ran far too large. Different ices sublimate at different temperatures, and that detail matters enormously. Carbon monoxide and carbon dioxide are what chemists call supervolatiles. They convert to gas at extremely low temperatures, far from any star. Water ice requires substantially more warmth before it joins the process. This explains why 3I Atlas was already active beyond Jupiter's orbit. Its carbon dioxide was boiling in cold that would keep water frozen solid. The activity detected months before discovery was supervolatiles abandoning an ancient body. That body had apparently been sitting below 30 Kelvin since before our Sun formed. Then the water joined in as the object fell closer to the Sun. NASA's Swift Observatory detected hydroxyl emission using its ultraviolet telescope. Hydroxyl forms when sunlight breaks apart a water molecule into fragments. Detecting hydroxyl therefore lets you measure water you cannot observe directly. The detection came at 3.51 astronomical units from the Sun. The production rate worked out to roughly 40 kilograms of water per second. Keep that number ready, because it climbed dramatically over the following months. By perihelion, the European Space Agency's JUICE spacecraft measured the outflow again. The rate had reached approximately 2 tons of water every second. That escalation from 40 kilograms to 2,000 took only a few months. That climb represents the object waking up after billions of years of sleep. It also represents the object actively destroying itself in front of us. Every gram that leaves that surface never returns to it again. 3I Atlas spent its perihelion passage converting itself into an expanding cloud. That cloud dispersed permanently into the interplanetary space around our Sun. The object departing our system is measurably smaller than the one that arrived. There is a second structure worth understanding alongside the dust. Comets typically display 2 quite distinct tails rather than one. The dust tail contains the solid grains we have been discussing. It curves gently because the grains retain some of the nucleus motion. The ion tail forms through an entirely different physical process. Ultraviolet sunlight strips electrons from gas molecules in the coma. Those molecules become electrically charged particles that respond to magnetism. The solar wind carries a magnetic field outward from the Sun. Charged particles get caught in that field and swept directly away. so the ion tail points almost exactly opposite the Sun. It appears straighter and often bluer than the dust tail beside it. Photographs showing two separate tails at different angles show exactly this. Keep those two structures separate in your mind for later. Some of the confusion about this object's appearance stems from conflating them. Reports of colour changes often described the gas rather than the dust. The two components genuinely can behave independently of one another. Sit with that for a moment, because the implication is genuinely strange. Some fraction of a body older than our Sun boiled off here. That material is now permanently mixed into the dust of our solar system. It is spread impossibly thin, and it will remain here indefinitely. Before we leave the mechanism, one more consequence deserves attention. All that escaping gas and dust carries momentum away from the nucleus. Momentum leaving in one direction pushes the nucleus in the other. This is precisely how a rocket engine operates in principle. A comet is therefore a very inefficient and entirely accidental rocket. The thrust is tiny compared to the mass being pushed, but that thrust operates continuously for many months at a time. Small forces applied for long periods produce measurable changes in trajectory. Astronomers call the result non-gravitational acceleration, and they measure it routinely. Comet Halley shows it, and Comet 67P shows it. Essentially every active comet ever tracked precisely displays this behaviour. The effect is expected, well understood, and entirely unremarkable in comets. 3I Atlas displayed exactly this behaviour near its perihelion passage. That measurement later became one of the more contested talking points. Remember tonight that the effect itself surprised nobody who studies comets. There is a subtlety that makes the measurement genuinely useful, however. The size of the acceleration depends on the mass being pushed. It also depends on how much material is escaping each second. Measure the outgassing and the acceleration together, and mass becomes accessible. That is one of the few routes to a nucleus mass estimate. It is indirect, it carries large uncertainties, and it is what we have. Direct measurement would require flying alongside and tracking gravitational influence. Material from another star system is now a permanent resident of ours, and the composition of that material turned out to be the real surprise, because when instruments analysed what was boiling off, the numbers made no sense. Part 7. The element that should have been there and was not. In the late summer of 2025, spectroscopy began returning results. Spectroscopy works by splitting light into its component wavelengths for analysis. Every molecule absorbs and emits at its own specific set of wavelengths. That pattern functions as a chemical fingerprint that does not vary. Sunlight passing through cometary gas returns stamped with whatever it touched. The technique is effectively a chemistry laboratory operating across hundreds of millions of kilometres. Observations from the Very Large Telescope in Chile detected something unexpected. They found atomic nickel vapour in the coma surrounding the nucleus. The detection came when the object sat 3.9 astronomical units from the Sun. Keck Observatory in Hawaii confirmed nickel emission alongside cyanide in late August. Two independent facilities were reporting the same unusual chemical signature. Here is why that finding raised eyebrows across the astronomical community. Nickel and iron are chemical siblings that travel together almost everywhere, in meteorites, asteroids, and planetary cores. They occur in predictable proportions. Where you find one of them, you reliably find the other nearby. 3I Atlas was showing nickel with no detectable iron alongside it. That is genuinely unusual, and it became one of the most cited oddities. For several months in late 2025 it dominated online discussion. I understand why that specific fact travelled as far as it did. Nickel sounds industrial to most people who encounter the word. Nickel is the metal that manufacturers plate other things with. Nickel appears in alloys, in coinage, and in stainless steel production. Finding it without its usual companion sounds vaguely manufactured rather than natural. Set that impression aside for 90 seconds and follow the chemistry instead, but there is an explanation, and I find it more interesting than the mystery. chemists work with a family of compounds called metal carbonyls. The relevant one here is a molecule called nickel tetracarbonyl. It consists of one nickel atom bonded to 4 carbon monoxide groups. It is a genuinely strange substance with a genuinely strange property. Discovered in the 1890s, it became industrially important for one reason. Nickel tetracarbonyl is volatile at remarkably low temperatures compared to metal. It turns to vapour around 43 degrees Celsius under ordinary conditions. It begins releasing measurable gas at temperatures considerably colder than that. Iron has an equivalent compound called iron pentacarbonyl with similar chemistry. That compound, however, requires noticeably more heat before it releases. So the two metals leave a cold body at different times. Picture a frozen body drifting slowly inward toward a distant star. As it warms, the nickel-bearing compound starts venting first into space. It requires less heat, so it reaches its threshold sooner. The iron-bearing compound stays locked inside the ice, waiting for more warmth. You observe nickel with no iron, but the iron has not disappeared. The iron simply has not been given permission to leave yet. That explanation carries a genuine, testable prediction about future observations. The prediction is straightforward, and it was checked directly afterward. As the object warmed further, iron should appear, and the ratio should normalise. Work led by Damien Hutzamkes examined exactly that question after perihelion. The nickel-to-iron ratio evolved toward ordinary cometary values as predicted. The technique underlying all of this deserves a brief explanation. In the early 1800s, Joseph von Fraunhofer examined sunlight carefully. He spread it into a spectrum and noticed dark lines within it. Hundreds of narrow dark gaps appeared at very specific wavelengths. Those gaps mark wavelengths absorbed by elements in the sun's atmosphere. Each element produces its own unique and entirely unchanging pattern. Sodium absorbs at one set of wavelengths and nothing else. Nickel absorbs at a completely different and equally specific set. That discovery turned ordinary light into a precise chemical analysis tool. It works identically whether the source sits nearby or across the galaxy. The physics does not change with distance in any respect. Astronomers determine the composition of stars they will never visit. Applied to a comet, the technique reads the gas around the nucleus. Sunlight passes through that gas and emerges carrying absorption signatures. Some molecules also emit light directly when solar radiation excites them. Both processes leave fingerprints that no other substance can imitate. So when researchers reported nickel in this coma, there was no ambiguity. The emission lines matched nickel and matched nothing else at all. The measurement was solid, and the interpretation was the difficult part. I want you to pay close attention to what just happened there. An observation that appeared impossible turned out to be a thermometer. The anomaly was not evidence of strangeness in the object's construction. It was evidence that the object was cold and steadily warming. The physics predicted the behaviour, and then the behaviour occurred on schedule. There is a broader point worth extracting from the nickel episode. Notice how that anomaly behaved as more information gradually arrived. It did not become stranger, and it did not deepen into mystery. It resolved into ordinary chemistry that had simply been unfamiliar. That same pattern recurs constantly throughout the history of astronomy. Pulsars were briefly labelled with the designation for little green men. The regular radio pulses seemed impossible to explain naturally at first. Jocelyn Bell Burnell detected the first one in 1967. Within roughly a year, rotating neutron stars explained the signals completely. The universe had produced something far stranger than anyone had expected. It had not produced anything artificial in the slightest degree. Quasars followed a very similar path during the 1960s. Objects appeared to release impossible amounts of energy from small volumes. The eventual explanation involved supermassive black holes consuming surrounding matter. Again, the reality was stranger than the initial confusion suggested. I raise these cases for a reason directly relevant tonight. The history of unexplained astronomical observations has one consistent pattern. The natural explanations, when they arrive, are almost always more interesting. They are rarely more comforting, and they are rarely simpler. Keep that lesson close, because you will need it within the hour. Not every anomaly on the eventual list dissolved that cleanly. Some of them proved considerably more stubborn under continued examination, and one of them, largely ignored by the public, is still standing tonight. But before we reach that, there is a simpler oddity to address. The most basic question about any comet concerns what it is made of, and on that question, 3i Atlas gave an answer nobody expected. Part 8. 8 parts fizz to 1 part water. On August 6, 2025, the James Webb Space Telescope observed. It pointed its near-infrared spectrograph directly at 3i Atlas. The object sat 3.32 astronomical units from the Sun. It remained beyond the asteroid belt, and it remained genuinely cold. What Webb found was a coma dominated overwhelmingly by carbon dioxide. On its own, carbon dioxide in a comet is entirely unremarkable. Every comet we have ever studied contains substantial quantities of it. The strangeness lives entirely in the ratio between those two compounds. In essentially every comet in our solar system, water dominates the volatiles. Water ice sublimates first and most abundantly as a comet warms. It drives the overwhelming majority of the activity we observe. Carbon dioxide is present, but always as a minority component. In 3i Atlas, the ratio ran 7.6 to 1. Carbon dioxide outnumbered water by nearly 8 to 1 by measurement. The team established that figure with an uncertainty of plus or minus 0.3. It sits 4.5 sigma outside the established comet trendline. That trendline covers both long-period comets and Jupiter family comets. Neither population comes anywhere near the value measured in this object. If our comets are mostly steam with some fizz, this reversed it. Water made up only a few % of the escaping mass. I want you to sit with how strange that inversion actually is. Every comet humanity has sampled behaves one way on this measurement. This object behaved the opposite way by a substantial margin. There are 2 explanations available, and researchers presented both carefully. Either the object genuinely formed with far more carbon dioxide than anything local, or its outer layers were processed by radiation during its interstellar journey. Stephanie Milam at NASA's Goddard Space Flight Center described a kind of cooked crust. That second possibility deserves unpacking, because it involves something we cannot study otherwise. Space between the stars is neither empty nor safe for anything travelling through. It is continuously swept by cosmic rays from supernovae and other violent events. These are atomic nuclei accelerated to a substantial fraction of light speed. They arrive constantly, from every direction, and they penetrate solid material. When such a particle strikes icy surface, it does not simply bounce away. It drives down into the material, breaking chemical bonds along its path. Molecules split apart, and the fragments recombine into entirely new compounds. Over sufficient time, this transforms the outer layers of any exposed ice. The surface becomes darker, more processed, and depleted in its original volatiles. It grows enriched in heavier organic residues left behind by the bombardment. Now consider the exposure time involved for this particular object. If it formed 7 billion years ago, the arithmetic becomes staggering. Its surface has endured continuous bombardment for longer than Earth has existed. That is billions of years of unshielded exposure to the galaxy. Nothing in our solar system carries that history in its surface layers. Our comets spend their lives in the Oort cloud or the Kuiper belt. They remain gravitationally bound to the Sun throughout their existence. They stay partially shielded by the heliosphere surrounding our entire system. The heliosphere is the vast bubble of solar wind pushing against interstellar space. Even at the outer edge, our comets remain inside something protective. An interstellar object enjoys no such protection at any point. It has been naked in the galaxy for its entire existence. Hold that image, because it changes how you read every measurement. So the carbon dioxide result supports two genuinely different stories. Either we are learning the chemistry of a completely different protoplanetary disk, or we are learning how the interstellar medium weathers whatever passes through it. Distinguishing between those two requires sampling below the processed outer layer. Sampling below the surface requires a spacecraft physically present at the object, and that requirement is the entire problem we will confront shortly. To weigh those explanations properly, consider how planetary systems form. A young star begins surrounded by a flattened disk of gas and dust. That flattened structure is what astronomers call a protoplanetary disk. Material within it gradually clumps together into progressively larger bodies. Temperature within that disk falls steadily as you move outward. Close to the star, only rock and metal can remain solid. Farther out, water ice becomes stable and joins the mixture. Astronomers call that boundary the snow line of the system. Beyond the snow line, more volatile compounds begin freezing out as well. Carbon dioxide freezes considerably farther out than water ice does. Carbon monoxide requires colder conditions still before it becomes ice. So the composition of any body records where in the disk it formed. A body rich in carbon dioxide relative to water formed beyond the water-dominated zone. A body rich in carbon monoxide formed farther out still. This is exactly why composition functions as a location record. 3I Atlas carries the signature of formation extremely far from its star. The Tianwen-1 dust result points toward exactly the same conclusion. Two entirely independent measurements agree on where this object assembled. There is one more scenario worth putting on the table here. The object might have formed around a star quite unlike our Sun. Stars vary enormously in mass, in temperature, and in chemical composition. A cooler star produces a colder disk with a closer snow line. A star poor in heavy elements produces a disk poor in them too. Any planets and comets forming there inherit that deficiency directly. So the chemistry we measured might simply reflect a different parent star. That possibility connects directly to the age question we reach later. Older stars formed when the galaxy contained fewer heavy elements overall. A comet from such a system would look chemically impoverished to us. It would look, in fact, roughly like what we measured. Notice that these explanations are not mutually exclusive in any way. The object could have formed far out in a cold disk. That disk could have surrounded an ancient and metal-poor star. Its surface could then have been processed for billions of years afterward. All three effects would push the composition in the same direction. Disentangling their relative contributions requires exactly the data we no longer have. It requires sampling material from beneath the processed outer layer. Both explanations remain plausible, and neither has been resolved to anyone's satisfaction. Neither can now be resolved by any observation we are capable of making. You should be noticing a pattern forming across these measurements. The instruments performed brilliantly and returned results nobody can follow up. Every one of these findings arrived with a permanent expiration date attached. The chemistry told us the object was strange without telling us why. And then a smaller team measured something even harder to explain away. Part 9. The light that came back the wrong shape. In September 2025, a team published a genuinely unusual measurement. Zuri Gray and Stefano Bagnolo led that work using multiple European facilities. They used the Very Large Telescope's FORS 2 instrument in Chile. They added data from the Nordic Optical Telescope and the Rosen Observatory in Bulgaria. They were measuring something less familiar than spectroscopy called polarization. Let me explain what that is, because it turns out to matter enormously. Light is a wave, and that wave vibrates in a particular orientation. Ordinary sunlight vibrates in all orientations at once, entirely randomly. Physicists describe that entirely random arrangement of light as unpolarized. When light bounces off a surface, something changes about that arrangement. The reflection then favors certain vibration orientations more than the others. The light becomes partially polarized as a result of that interaction. This is not exotic physics confined to any specialist laboratory. It explains why polarized sunglasses cut glare reflecting off water. It explains why camera filters change how a blue sky appears. You have used this physics without ever thinking about it. Now here is the part that makes it scientifically valuable. How much a dust cloud polarizes light depends on the grains involved. It depends sensitively on their size, shape, structure, and composition. Measure polarization across a range of viewing angles and you learn about the dust. You learn things no photograph could ever reveal about those particles. Every comet and asteroid we have measured shows a characteristic pattern. At small viewing angles, the polarization dips slightly negative into a shallow trough. Then it climbs back through zero at what astronomers call the inversion angle. That inversion typically occurs somewhere around 20 degrees of phase angle. This pattern holds across essentially every small body ever measured. 3I Atlas did not follow that pattern at all. It produced a negative polarization branch reaching minus 2.7%. That minimum occurred at a phase angle of roughly 7 degrees. The inversion angle came in around 17 degrees rather than 20. Both the depth and the narrowness fell outside all previous measurements as unprecedented among asteroids and comets. They explicitly included 2I Borisov in that comparison for context. So this was not simply a general characteristic of interstellar bodies. Even the other interstellar comet did not behave this way. Do not lose track of that detail, because it survives everything that follows. That result appeared in the Astrophysical Journal letters after peer review. It has not been retracted, explained away, or quietly resolved since publication. It is worth explaining what large dust grains actually imply. Grain size in a comet reflects the conditions during accretion. Fine grains dominate where material was processed and reprocessed repeatedly. Coarse grains survive only where material was left largely undisturbed. In the inner regions of any disk, collisions happen frequently. Particles grind against one another and fragment into smaller pieces. Radiation from the young star also processes exposed surfaces heavily. The result is a dust population dominated by very fine material. Far from the star, collision rates drop dramatically with distance. Particles have room and time to grow without being shattered. Radiation processing also weakens as the star's light spreads thinner. Larger, fluffier aggregates survive intact for the lifetime of the system. So finding grains hundreds of microns wide points somewhere very specific. It points to the frozen outskirts where nothing much ever happened. It agrees with the carbon dioxide dominance we examined earlier. It agrees with the deuterium measurement we have not yet discussed. 3 separate lines of evidence converge on the same conclusion. This object assembled in the coldest, quietest region of another system. Then something ejected it out of that system into interstellar space. Let me summarize where the evidence stood at the midpoint of the encounter. We had a body from another star system with striking chemistry. Carbon dioxide outnumbered water roughly 8-1 in its coma. Dust grains ran hundreds of microns across rather than micron scale. Nickel appeared without iron until warming released the iron on schedule. The nucleus stayed unresolved, uncertain by a factor exceeding 10. And the polarization signature matched nothing ever recorded in astronomical literature. I want to add one more measurement before the summary. The object's activity began at a genuinely remarkable distance from the Sun. Dust was streaming off it at 6.4 astronomical units. That figure keeps recurring because of what it rules out. Water ice does not sublimate meaningfully at that distance from the Sun. The surface temperature there sits far too low for it. Something else was driving that activity in the deep cold. Carbon dioxide and carbon monoxide were the only realistic candidates. Now consider what the object had been doing before that point. It had been travelling through interstellar space for billions of years. Temperatures there hover only a few degrees above absolute zero. Nothing sublimated, nothing changed, and nothing moved on that surface. Then, for the first time in its entire existence, it warmed. Sunlight from a star it had never encountered began depositing energy. Ices that had been stable since before our sun formed began converting. Everything we measured was that awakening, captured across a few months. The coma, the tails, the jets, and the dust were all one event. It was the first and only time that body ever became active near a star. Any one of those findings would justify a decade of follow-up study. Together they describe an object worth an entire dedicated mission. And every single one of them was measured against a closing deadline. Because within weeks of these observations, we were going to lose sight entirely. The geometry that gave Mars such a spectacular view had another consequence. For everybody standing on Earth, that consequence was considerably less helpful. Part 10. The weeks our whole planet went blind. Here is the cruelty built into the orbital arrangement of this encounter. The most valuable period of the entire visit was perihelion week. That is when the object ran hottest and vented the most material. It revealed more about its interior then than at any other time. During that exact window, 3I Atlas was invisible from Earth. The object passed behind the Sun from our line of sight. Astronomers call that solar conjunction, and it defeats every ground-based instrument. Looking that close to the Sun blinds any telescope attempting it. Hubble could not look, and the James Webb Space Telescope could not look. Every observatory on every mountaintop on this planet faced a wall. The single most informative moment of a once-in-a-lifetime event happened behind a curtain. This is precisely why the Mars spacecraft mattered as much as they did. They were not a novelty or a pleasant scientific bonus. For several critical weeks they were our only functioning eyes. Machines orbiting another planet carried the entire observational burden alone. Tom Statler at NASA described the arrangement rather beautifully afterward. He said it was a little like their spacecraft attending a baseball game. Each one watched from a different place in the stadium, he explained. Every seat gave a partial view of the same play. Let me walk through who occupied that stadium, because the list is remarkable. Count the flags on this list as I go through it. NASA's Mars Reconnaissance Orbiter photographed the comet on October 2nd. It used HiRISE, the most powerful camera ever sent to another planet. Physically, that orbiter was the closest NASA asset to the object. China's Tianwen-1 captured the 57 frames we opened with tonight. The European Space Agency's ExoMars Trace Gas Orbiter observed from October 1st. Its campaign ran through October 7th using the CASSIS imaging system. That orbiter accomplished something with genuine practical consequence for everyone. Its astrometry, meaning its precise position measurements, entered the Minor Planet Center database. Those were the first such measurements from a spacecraft orbiting another planet. They improved our knowledge of the object's path by roughly a factor of 10. NASA's MAVEN orbiter watched in ultraviolet from September 27th onward. Its observations continued through October 7th, detecting cometary hydrogen by velocity signature. The Perseverance rover looked up from Jezero crater on October 4th. A machine standing on Martian ground photographed an object from another star. The United Arab Emirates Hope orbiter contributed additional ultraviolet observations. Further out, other spacecraft joined the improvised campaign as well. NASA's Psyche mission observed 4 times over 8 hours in September. It was travelling toward a metal asteroid roughly 33 million miles away. The Lucy mission observed, as did Parker Solar Probe and Stereo A. Researchers even repurposed solar coronagraphs aboard SOHO and GOES satellites. Those instruments block the sun's disk to study its outer atmosphere. Qishong Zhang and Carl Battams used them to track the comet's brightening. They converted solar monitoring instruments into comet trackers out of pure necessity. There was simply no alternative available during those conjunction weeks. And then there is the story of JUICE, which I find genuinely poignant. The European Space Agency's Jupiter Icy Moons Explorer observed around perihelion, but JUICE could not transmit any of that data home, The spacecraft was using its high-gain antenna as a heat shield. That dish pointed toward the sun to protect the instruments behind it. Pointing it at Earth instead would have cooked those instruments directly. So JUICE recorded superb observations and then sat silently on them. The data was not downlinked until February of this year, 2026. 4 months of silence, caused entirely by thermal engineering rather than science. When it finally arrived, the results justified the wait completely. Pasquale Palumbo is principal investigator for the Janus camera aboard JUICE. He reported an extended coma, a tail, and various structural features. Those included rays, jets, and filaments visible in the processed imagery. The water outflow measured approximately 2 tons every second at that point. I want you to feel the scale of what those instruments recorded. David Jewett's team measured dust production at 2 astronomical units. The rate came in around 180 kilograms per second. At that same distance too, Borisov produced roughly 70 kilograms per second. So this object shed material more than twice as fast as its predecessor. It was actively falling apart while we watched through borrowed instruments, and redirecting all those instruments cost far more than most people realise. Time on major observatories is allocated a year or more in advance. Astronomers submit competitive proposals, and committees rank them against each other. Successful applicants receive a handful of hours, sometimes only minutes. Oversubscription on the best instruments runs at 5 or 6 to 1. Entire careers get built around a few allocated nights of observation. Observing something discovered after the schedule was written requires special permission. Observatories hold back a small emergency reserve called Director's Discretionary Time. Requesting it means asking that somebody else's planned observation be delayed. That happened repeatedly throughout the second half of 2025. The ULMA observations that produced the deuterium measurement ran under discretionary time. Webb time was reallocated, and Hubble time was reallocated as well. Behind every observation sits a researcher whose own project slipped a cycle. With spacecraft, the calculation grows harder still, for physical reasons. A spacecraft carries a finite budget of every consumable it needs: fuel for attitude control, thermal cycles on instruments, and onboard data storage. Downlink bandwidth through the deep space network is shared and chronically overbooked. Slewing Tianwen-1 spent propellant that will never be available again, pointing Psyche at the Comet cost observation time from its primary mission. Every decision came from people spending resources they could not replace. Across at least 5 space agencies, independently, dozens of teams reached one conclusion. No treaty coordinated them, and no committee instructed them what to do. Separate groups looked at the same faint dot and decided it mattered. Then, in the middle of all this, the United States government shut down. From October into November 2025, NASA effectively went silent. The cause was an ordinary budget failure unrelated to any comet. Public affairs stopped, and scheduled image releases stopped along with them. The Mars Reconnaissance Orbiter photograph from October 2nd sat unreleased for weeks. Into that silence poured every conspiracy theory you could reasonably imagine. The absence of data was widely read as deliberate suppression of data. None of that was true, and the reality was considerably more mundane. A funding lapse silenced an agency holding something genuinely extraordinary. The resulting vacuum filled itself with noise, as vacuums generally do. NASA finally held a briefing at Goddard on November 19th. Amit Kshatriya, an associate administrator, summarized the agency position in one sentence. "It looks and behaves like a comet," he said plainly. "All evidence," he added, "points toward it being exactly that." But by then, a very different conversation had taken hold publicly, and the measurements arriving quietly in the background were far more astonishing. Because while the public argued about spacecraft, the isotopes were saying something else. Part 11. The water that formed before the sun existed. Stay with me through the next section, because it requires some chemistry. This is, in my judgment, the actual story of 3I Atlas. It got buried underneath a very loud argument about alien technology. Hydrogen comes in two stable varieties found throughout the universe. Ordinary hydrogen carries a nucleus consisting of a single proton. Deuterium, sometimes called heavy hydrogen, carries a proton and a neutron. Chemically, the two varieties behave almost identically in every reaction. That similarity is why heavy water exists and looks entirely normal. Heavy water is water where deuterium replaces one or both hydrogen atoms. It is real, it is stable, and it looks like ordinary water. The ratio of deuterium to ordinary hydrogen functions as a temperature record. The colder the environment where water formed, the more deuterium becomes locked inside. The chemistry that concentrates deuterium runs efficiently only at extremely low temperatures. It shuts down almost entirely as the environment warms up. Measure that ratio in a comet, and you read a frozen thermometer. It records conditions from the moment that material first came together. We have measured this ratio in dozens of solar system comets. Halley, Hale-Bopp, and Comet 67P have all been sampled. They cluster within a recognizable range that defines normal for our system. Earth's oceans sit within a related range on the same scale. Comparing them is part of how we investigate where our water originated. The measurement for 3I Atlas used two separate world-class facilities. ALMA, the Atacama Large Millimeter Array in Chile, provided one dataset. The James Webb Space Telescope provided the other independent measurement. Results appeared in Nature and Nature Astronomy earlier this year. Martin Cordner at NASA Goddard was among the lead authors involved. The water-deuterium ratio came in at 0.98%. The stated uncertainty was plus or minus 0.06. I need you to understand how far outside normal that value sits. It exceeds any comet ever measured in our solar system substantially. It runs roughly 30 times higher than any local comparison available. It runs about 40 times the value found in Earth's oceans. The water inside that object was 40 times more deuterium-rich than seawater. The team measured methane as well, finding a ratio of 3.31%. Then they measured carbon isotopes, which tell a related story. The ratio of carbon-12 to carbon-13 ranged between 141 and 191. That measurement came from the carbon dioxide in the coma. For carbon monoxide, the range ran from 123 to 172. Cordner summarized the finding in terms that are worth quoting directly. What they were seeing, he said, did not match our own solar system. It did not match our own comets in any respect. It did not match any nearby protostars either, he went on. This, in his own words, was something genuinely new and different. So what do those numbers actually mean in physical terms? There are two implications, and the second one is genuinely staggering. First, the water in it formed at or below 30 Kelvin. 30 Kelvin equals roughly minus 243 degrees Celsius. That temperature sits 30 degrees above absolute zero, the coldest possible state. That is not the outer edge of an ordinary planetary system. That is the deep dark between stars, or the frozen fringe of a disk. Second, the carbon isotope ratios point toward a metal pore formation environment. The universe began with almost nothing except hydrogen and helium. Every heavier atom was manufactured inside stars and scattered by their deaths. Carbon, oxygen, nickel and iron all originated inside stellar furnaces. So heavy element abundance has been climbing across 13.8 billion years. A metal poor environment is therefore, by definition, an old environment. These measurements remain consistent with material assembling 12 billion years ago. Let me put 12 billion years into terms you can genuinely feel. Our sun formed roughly 4.5 billion years ago. The earth beneath your feet formed at the same time. Every mountain, ocean, fossil and rock dates from that period. This object may have assembled more than twice as long before that. Hold that comparison, because nothing else in this story matches it. and an entirely independent method reached the same conclusion separately. Matthew Hopkins at Oxford defended his doctoral thesis 1 week before discovery. His work with Chris Lintott at Oxford and Michelle Bannister at Canterbury modelled populations. They built a statistical model of interstellar objects passing through our system, feed in velocity and trajectory, and it identifies the likely source population. Their answer pointed toward the Milky Way's thick disk of stars. The thick disk is the older, puffier population above and below our plane. Our Sun lives in the thin, orderly disk where younger stars gather. The thick disk is where the galaxy keeps its ancient members. Hopkins stated the implication quite plainly in his public comments. All non-interstellar comets formed alongside our solar system, he explained. They are therefore up to 4.5 billion years old. Interstellar visitors, he noted, have the potential to be far older. Their statistical methods suggested this was very likely the oldest comet ever seen. Lintott framed the same results slightly differently in his own remarks. There is roughly a 2/3 chance the comet predates our solar system. It comes, he said, from a part of the galaxy never observed closely. 2 independent methods, one statistical and one chemical, reached one conclusion. Statler at NASA responded to that convergence in memorable terms. It means the object is not just a window into another solar system, it is a window into the deep past, he explained. So deep that it predates the formation of our Earth and Sun. That thought, he admitted, gives him goosebumps to consider. I do not consider that an overstatement of the situation. It seems a restrained reaction to handling something older than your planet, and that object passed through our neighbourhood for roughly 4 months. It is now departing at 58 kilometres per second. Permanently, no human being will ever touch it, sample it or resolve it. So the conversation should obviously have focused on all of this. Before we turn to that argument, hold one comparison in mind. Every dating method we have applied to this object agrees. The statistical population model points toward the ancient thick disk. The deuterium ratio points toward formation somewhere below 30 Kelvin. The carbon isotopes point toward a galaxy poor in heavy elements. 3 independent techniques, resting on entirely different physics, all converge. That kind of convergence is what scientists mean by a robust result. It is far stronger evidence than any single measurement could provide, and that convergence means something rather difficult to absorb properly. For roughly 4 months, an object assembled before our Sun existed passed nearby. It came within the orbit of Mars and then departed permanently. That happened during a period most people spent arguing about something else. It did not, and understanding why requires examining a very public argument. Part 12. The argument that ate the evidence. I want to handle this section carefully, because being cheap serves nobody. Avi Loeb is a professor of astrophysics at Harvard University. He formerly chaired Harvard's astronomy department for a considerable period. He directs the Institute for Theory and Computation there today. He also heads a research effort known as the Galileo Project. He is not a fringe figure by any reasonable measurement. He has published hundreds of peer-reviewed papers across a long career. He is also the person who, within weeks of the discovery, began cataloguing anomalies. He raised publicly the possibility that this object might not be natural. His list started at around 13 separate items of concern. It grew to 14, then 18, and eventually to 22 anomalies. These appeared across a long sequence of essays published on Medium. In July 2025, he also co-authored a preprint with 2 colleagues. Adam Hibbard and Adam Kroll joined him in asking whether it was technology. Let me lay out his strongest points honestly rather than selectively. Presenting only the weak arguments would be steering you rather than informing you. His first point concerned the geometry of the object's arrival. He calculated that the trajectory passed unusually close to several planetary orbits. Mars, Venus and Jupiter all featured prominently in that particular calculation. He noted it reached perihelion while hidden from Earth behind the Sun. He assigned that combination a probability of roughly 5 in 100,000. He characterized the resulting arrangement as suspiciously fine-tuned for a natural body. his second point gained substantially more traction than the first. Remember that Jupiter figure I asked you to hold earlier tonight? The forecast closest approach measured 53.56 million kilometres. Jupiter's Hill radius measures approximately 53.5 million kilometres. The Hill radius marks the boundary of a planet's gravitational domain. Inside it, the planet's pull dominates over the Sun's influence. Loeb assigned that near identity a probability of 4 in 100,000. He speculated it could indicate the release of devices near Jupiter's Lagrange points. His third point concerned the sunward jet visible in Hubble imagery. The July 21st image showed material extending toward the Sun. That direction is opposite to where a normal tail should point. Loeb interpreted that structure as a collimated jet of unusual proportions. He described it as roughly 10 times longer than it was wide. He estimated its extent at around 400,000 kilometres. Then came the chemistry, which we have already examined in detail. The carbon dioxide dominance featured prominently near the top of his list. So did the nickel without iron and the extreme deuterium fraction. The bluer than expected colour measured near perihelion appeared on that list as well. Now 3 things need saying, and I intend to say all 3. The first is that Loeb has consistently hedged his claims. That fact gets lost almost entirely in popular coverage of him. His repeated formulation is that the most likely outcome is natural. By far, he has written, this is probably simply a comet. He built a 0 to 10 scale for rating artificiality likelihood. He rated 3I Atlas a 4 on that scale. That is not a claim of alien contact by any reading. It is a claim that a possibility deserves examination before dismissal. The second point is that his stated principle is entirely reasonable. When challenged, he responds that truth is not decided by authority. Nor is scientific truth decided by popularity, he argues in response. It is decided instead by careful attention to the available data. I have no argument with that sentence, and neither should anyone. The third point is, where I have to be direct with you. The astronomical community examined these claims and rejected them firmly. They did so with unusual bluntness for a professional discipline. Chris Lintott at Oxford, who co-authored the age model we discussed, responded sharply. Any suggestion the object is artificial, he said, is nonsense on stilts. It is an insult, he added, to the exciting work underway. Darrell Seligman addressed the specific claim regarding non-gravitational acceleration directly. Comets experience non-gravitational accelerations all the time, he pointed out. It would be almost strange, he said, to imagine one without them. He noted numerous telescopic observations demonstrating classical signatures of cometary activity. Samantha Lawler offered a measured but firm assessment of the preprint. Remaining open-minded about any testable prediction is important, she readily acknowledged. But this paper, she said, pushes that sentiment to its limit. The evidence presented, in her judgment, was absolutely not extraordinary. Jason Wright at Penn State identified specific technical flaws publicly. David Kipping raised separate objections to the statistical reasoning involved. Multiple researchers independently identified problems with the underlying trajectory analysis. The European Space Agency treated the entire episode rather differently. Richard Meusel heads that agency's Planetary Defense Office in Germany. His framing turned the entire affair into something genuinely useful. Using Mars-based data for an unusual observation taught them a great deal. They learned more about the comet's path through the solar system. It was, he said, a valuable test case for planetary defense. The object posed no danger, he emphasized clearly and repeatedly. Having exercised the communication and interface channels made them confident. They could perform the same activities, he said, for a genuinely threatening object. That quiet outcome may be the most practical result of the whole affair. The United Nations affiliated International Asteroid Warning Network ran a formal exercise. It was their 8th such observing campaign, using this comet as the target. It ran from November 27th, 2025 to January 27th, 2026. They used a harmless interstellar visitor as a live fire drill. The rehearsal targets the day something arrives that is not harmless. Watch what happened to the anomalies themselves over those same months. The nickel without iron dissolved into ordinary chemistry, as we established. The colour change largely dissolved under closer examination as well. Chichen Zhang at Lowell Observatory pushed back on that reporting directly. "There is no evidence for the gas coma changing colours," he said. "The comet changed colour once, when its gas coma first became bright. You were watching a second light source switch on, not an object transform. Separate work from the University of Hawaii found colours stable across 3 months. A real scientific tension remains there about the precise behaviour. But it is a disagreement about photometry, not evidence of engineering. The sunward jet has a conventional explanation we already covered. Return to the paper and the brick from the opening. Sunlight simply cannot blow a house brick backward against gravity. When a comet ejects unusually coarse material, that material resists the push. It hangs on the sunward side, forming a fan rather than a tail. Peer-reviewed work by David Jewett's group describes exactly that structure. The 2-meter twin telescope campaign reported the same finding independently. Both attributed it to large, compact dust grains resisting radiation pressure. The rotation claim requires a specific correction that circulated very widely. You may have seen reports that the object dramatically spun up. Those reports described a change from 16 hours to about 7. The peer-reviewed rotation period, measured by Santana Ross and colleagues, is different. It stands at 16.16 hours, with tiny stated uncertainty. Independent work by other teams placed it near 16.8 hours. The 7-hour figure comes from blog analysis of jet precession. Loeb himself notes it is shorter by a factor of about 2.3. He attributes it to a possible doubling of the jet modulation frequency. That is a very different statement from the nucleus spinning twice as fast. That figure was never peer-reviewed as a genuine change in rotation. Anonymous accounts amplified it into something the original analysis never claimed. So a clear pattern emerges from examining these anomalies over time. Those with conventional explanations available received them as data accumulated. The polarization result, which almost nobody discussed publicly, still stands unexplained. The strangest measurable thing about this object was never the thing being argued about. And that brings us to the moment somebody stopped arguing entirely. Part 13. 7 hours of listening to absolutely nothing. In July 2025, a team did the obvious and neglected thing. Sophia Sheikh at the SETI Institute led that particular effort. They stopped speculating about the object and simply ran an experiment. They used the Allen Telescope Array at Hat Creek in Northern California. They observed 3i Atlas across 5 separate sessions that month. Total observing time came to 7.25 hours. Frequency coverage ran from 1 GHz up to 9 GHz. Let me explain what such a search actually involves in practice. The raw numbers are extraordinary, and they rarely reach popular coverage. The array recorded, and their analysis pipeline detected, roughly 74 million narrowband hits. That total came from just 7.25 hours of observation. A hit is any narrow signal standing out above the background noise. Almost every single one of them originates from our own technology. Radar systems, satellites, aircraft transponders and mobile infrastructure all contribute. Our own civilization is deafeningly loud across the radio spectrum. Any search for signals from elsewhere is primarily an exercise in self-subtraction. Filtering brought 74 million hits, down to roughly 2 million candidates. Further filtering then checked whether those signals drifted in frequency appropriately. A genuine transmitter moving with the comet would show a characteristic drift. That test brought 2 million candidates down to 211. Those final 211 were inspected individually by human beings. Their published conclusion consists of one single flat sentence of text. They did not find any signals worthy of additional follow-up. Nothing appeared across 8 GHz of bandwidth over those hours. The third interstellar object ever discovered was completely and entirely silent. But the part that gives that silence real weight comes next. The team calculated the minimum transmitter power they could have detected. That figure came out between 10 and 110 watts. 10 watts is roughly the power draw of a household appliance. It is roughly a bright light bulb, or less than a phone charger. Anything aboard that object broadcasting at lamp power would have been heard. Nothing was heard across every single frequency that they examined. An earlier search using the Meerkat array in South Africa went further. It reached a sensitivity limit around 0.17 watts. The researchers compared that threshold to a single cell phone handset. The Allen Telescope Array search was less sensitive in raw power. It compensated by covering 10 times more of the radio spectrum. Between the two campaigns, a great deal of ground was covered. Both campaigns found a great deal of absolutely nothing at all. Sheikh explained why the exercise mattered in terms worth hearing fully. Eventually our own Voyager spacecraft will be artifacts in other stellar systems, she noted. Given that, understanding the natural distribution of interstellar objects becomes important. Only then could we identify anomalies signalling something genuinely artificial. That is exactly the correct attitude toward a genuinely difficult question. She is not dismissing the question as unworthy of attention. She is arguing it deserves proper capability rather than speculation. Answering it properly means first establishing what normal actually looks like. Her co-author Valeria Garcia Lopez added a point that stayed with me. The results, she said, show how realistic detection has become. We could find a signal with the technology available today. What that search establishes is a standard, and standards were missing here. For most of the past decade, this argument ran on assertion. Somebody notices something unusual and then publishes their own interpretation. Somebody else offers a conventional explanation for the same observation. Neither side settles anything, because no agreed procedure exists for settling it. Sheikh's team did something structurally different from that familiar pattern. They defined a measurable threshold before making any observation at all. They ran the campaign, published the negative result, and stated the limit precisely. Anyone arguing the object was transmitting must now explain the silence. They must explain why it broadcast below light bulb power, or why it used frequencies outside that entire examined range, or why it stayed quiet during those particular 7 hours. That is what a genuine constraint looks like in practice. It does not close the question, and nobody claims that it does. It narrows the question permanently for everyone who comes afterward. The next investigation starts from a smaller space than this one did. Weigh that one outcome carefully against everything the public argument produced. I would argue that method is the most durable outcome here, not the answer itself, but the procedure for pursuing answers. The next interstellar object arrives to a published pipeline and demonstrated capability. That work will not have to begin again from nothing. It is worth asking why they chose those particular frequencies. The range from 1 to 9 GHz covers a specific region. Radio astronomers sometimes call part of it the water hole. That name refers to the wavelengths where hydrogen and hydroxyl emit. Those two components together make up a single water molecule. The region between them is unusually quiet in natural background terms. Interference from natural galactic sources drops noticeably across that band. Earth's atmosphere also transmits those wavelengths with relatively little absorption. For decades, researchers have argued that band makes an obvious meeting place. Any civilization attempting deliberate contact would face exactly identical physics. The quiet window exists for everyone in the galaxy equally. Searching there is a reasonable bet rather than an arbitrary choice. Whether that reasoning actually holds is genuinely debatable among specialists. It assumes a transmitter wanting to be found by someone. It assumes some shared logic about which frequencies seem obvious. Those assumptions may be entirely wrong in ways we cannot test. But the practical value of the search does not depend on them. The team established what was not there across 8 GHz. That measurement stands regardless of anyone's assumptions about alien motive. And the absence of a radio signal proves nothing about origin. A rock is silent, and so is a derelict machine. Something switched off 1 billion years ago transmits nothing at all. The null result eliminates one hypothesis, rather than every hypothesis. But combine that silence with everything else we have established tonight: classical cometary activity, measured dust production rates, and a growing coma. Jets, tails and water outflow reaching 2 tons per second. Nickel behaving precisely as volatile carbonyl chemistry predicted it would. Its chemistry stayed consistent with a cold, ancient metal-poor formation environment. An orbit requiring nothing beyond gravity and ordinary outgassing to explain. The weight of evidence was never distributed evenly across the possibilities. And while that argument consumed the public conversation entirely, something else happened. A small group of researchers ran a completely different calculation quietly. What they found disturbs me considerably more than any alien hypothesis. Part 14. The number that nobody wanted to publish. The paper carries an almost aggressively dry title for what it contains. It examines the feasibility of a spacecraft flyby with 3i Atlas. The authors considered departures from either Earth orbit or Mars orbit. Yaginuma, Frinker, Seligman, Mant, Della Giustina, and several colleagues wrote it. It appeared in the Astrophysical Journal after normal peer review. Let me establish one piece of vocabulary before the finding lands. Everything in spaceflight hangs on a quantity called delta V. The phrase means change in velocity, and it is the fundamental currency. Every maneuver a spacecraft performs costs some amount of delta V. Getting off the surface of Earth costs about 9.5 kilometres per second. Travelling from low Earth orbit to Mars costs roughly 4 more. A spacecraft's entire operational life is a fixed budget of delta V. That budget is determined at launch by fuel quantity and engine efficiency. When the budget runs out, the mission is finished permanently. You cannot refuel a spacecraft anywhere beyond low Earth orbit. So the question that team asked was refreshingly simple to state. Starting from Discovery Day, how much delta V would interception require? Departing from Earth immediately after discovery, the answer was 24 kilometres per second. That figure represented the best case available under entirely ideal conditions. Let me anchor that figure against something you already know. The Saturn V rocket remains the largest vehicle ever successfully flown. It carried human beings to the moon between 1969 and 1972. Across all its stages, it delivered roughly 17 kilometres per second. That performance sent a small capsule to the moon and nothing further. The requirement here was 24 on top of escaping Earth entirely, and the requirement climbed steadily with every week that passed. By early October, the figure had risen to about 35 kilometres per second. By December 2025, it stood near 60 kilometres per second. By January of this year, it had reached roughly 80. I want you to understand why those numbers are genuinely brutal. The natural assumption is that you simply add more fuel to compensate. That assumption is wrong, and understanding why is the key to everything. A Russian schoolteacher named Konstantin Tsiolkovsky worked this out in the 1890s. The rocket equation describes how delta V relates to propellant fraction. The relationship between the two is not linear in any sense. It is exponential, and exponential relationships punish ambition quite savagely. Let me make that concrete with a good chemical rocket engine. To match your own engine's exhaust speed, 2/3 must be propellant. To achieve twice that speed, roughly 86% must be propellant. 3 times, and you are looking at 95% propellant. 4 times, and you need about 98% of everything launched. That leaves 2% for tanks, engine, structure, power, and instruments. Every increment costs exponentially more than the increment before it did. This explains why rockets look the way that they do. It explains why they are built in stages that get discarded. It explains why useful payload delivered to another planet stays tiny. The mass on the launch pad dwarfs whatever arrives at the destination. So when the requirement climbed from 24 to 80, something specific happened. That is not a mission becoming progressively harder to accomplish. That is a mission passing from difficult to expensive to genuinely impossible. It made that journey in 4 steps across roughly 6 months. At 80 kilometers per second, chemical propulsion returns no useful answer. The propellant fraction you would need exceeds 100% entirely. The equation does not return a difficult number for that case. It returns nonsense, because no configuration of matter satisfies it. There is no rocket, and no amount of money changes that fact. I want to be fair to the people who tried thinking around this. After Oumuamua appeared in 2017, researchers ran serious studies. Those studies became known collectively as Project Lyra among specialists. They asked what chasing an interstellar object would genuinely require. The proposals were inventive rather than fanciful in any way. Solar sails featured heavily, using sunlight itself rather than carried propellant. Extreme close passes to the sun featured in those studies as well. A spacecraft would dive inward to within a few solar radii. It would then fire its engine at the moment of closest approach. That particular technique carries a name that is worth knowing. It is called an Oberth maneuver, after the theorist Hermann Oberth. The principle is that burns work better when you already move fast. Kinetic energy scales with the square of velocity rather than linearly, so burning at the bottom of a gravity well extracts far more energy. The same fuel produces dramatically more velocity change under those conditions. It is elegant physics, and it genuinely works as described. It is also enormously demanding on materials and mission design. Passing within a few solar radii requires heat shielding at material limits. The entire mission must be built around one burn at one moment. There is no second attempt available if anything at all goes wrong. The Project Lyra studies reached a sober and careful conclusion. Intercepting an object like Oumuamua was indeed possible in principle. It would require mission durations measured in decades of flight. It would need propulsion technology requiring serious further development first. Those papers were neither fantasy nor wishful thinking by any measure. They were also, when 3i Atlas appeared, entirely useless. You cannot develop a decade of propulsion in 120 days. The studies existed on paper, and the hardware did not exist anywhere. Then, the same team produced the finding I cannot stop thinking about. Launching from Mars rather than Earth changed the entire calculation. Between July and September 2025, the requirement dropped dramatically. The delta V needed fell to roughly 5 kilometers per second. Let me say that number again, because it should not be possible. 5 kilometers per second against 24 from Earth at the same moment. They worked a specific case to demonstrate the point concretely. A departure from Mars on August 10th would require 6.5 kilometers per second. That particular mission would produce a flyby on October 4th. The cruise would last 54 days from departure to encounter. Compare those two figures one more time before we continue. Every one of those numbers sits within ordinary engineering capability. 5 to 6.5 kilometers per second is not exotic at all. We have flown that kind of budget dozens of times already. It falls within chemical propulsion that existed in the 1970s. The reason for the difference is pure orbital geometry rather than technology. At the time of the encounter, Mars sat at nearly the right position. It occupied almost exactly the correct orbital longitude for departure. Earth sat on the far side of the Sun entirely. We were standing roughly 180 degrees out of phase. Mars was standing in very nearly the best available position. That accident of timing decided what was possible and what was not. So let me state where we actually ended up as plainly as possible. For a window of a few weeks in late summer 2025, an opportunity existed. Humanity could have flown a spacecraft past a 12 billion-year-old object. The propulsion technology was not the obstacle at any point. The physics was not the obstacle either, and the mathematics said yes. The obstacle was that nothing sat at Mars ready to depart. No probe waited in any storage facility with an unassigned mission. No launch vehicle stood stage for an opportunity nobody had predicted. No spacecraft existed anywhere with fuel in its tanks, and no destination. Researchers discussed hypothetical candidates after the fact, entirely on paper. A small spacecraft called Janus, built and then shelved when its mission was cancelled, came up. That discussion happened months after the window had already closed. The window was open, and nobody was standing anywhere near it. That is the actual story of 3i Atlas, in my judgment. The question was never whether the object was alien technology. The question was whether we were ready for it, and we were not. And this was not the first time we had received this exact lesson. Part 15. The 2 that came before, and the 50 still coming. To understand how badly this went, examine the 2 previous attempts. We had been warned twice before 3i Atlas ever arrived. October 19th, 2017, at a telescope on Haleakala in Hawaii. The Pan-STARRS survey detected a fast-moving object in its data. Robert Werrick identified it as something genuinely unusual within days. The orbit analysis came back hyperbolic, exactly as it would 8 years later. Humanity learned for the first time that objects from other systems pass through. It was named One-Eye Oumuamua from a Hawaiian phrase. The word suggests a scout, or a messenger reaching us from far away. And it was profoundly strange in ways that still resist explanation. It showed no coma, no tail, and no visible outgassing whatsoever. Its brightness varied so dramatically that the shape had to be extreme. Something far longer than it was wide seemed the only explanation. Yet despite showing no visible venting, its path was being altered. A small non-gravitational push was measurably altering its trajectory over time. That combination launched the entire modern argument about interstellar objects. Acceleration without any visible exhaust demanded some kind of explanation. Avi Loeb and Shmuel Billy published a paper addressing exactly that. The acceleration could be explained by radiation pressure on a thin surface. A light sail would produce precisely that behaviour, they argued. Possibly, they suggested, the object was genuinely artificial in origin. The competing natural explanations took several years to develop properly. Track how long the natural answer took to arrive here. Alan Jackson and Stephen Desch proposed a genuinely clever alternative. Oumuamua might be a fragment of nitrogen ice from another system. It could have been chipped off a Pluto like World's frozen surface. Nitrogen ice sublimates without producing the dust that makes a visible coma. That would explain acceleration occurring without any observable tail at all. They calculated dimensions of roughly 45 by 44 by 7 meters. That describes something closer to a cosmic pancake than a cigar. Here is a detail about that shape which deserves far more attention. Nobody ever photographed Oumuamua as anything except a point of light. No telescope at any moment resolved it into an actual shape. Every artist's impression you have seen is exactly that, an impression. The single line of evidence was the brightness curve over time. As the object rotated, its brightness rose and fell substantially. The size of that variation indicates the ratio of its dimensions. A sphere produces no variation, while a brick produces a great deal. Oumuamua's brightness varied by roughly a factor of 10 in total. That implied something 6 to 10 times longer than it was wide. But a light curve cannot distinguish a cigar from a pancake. Both of those shapes produce similar brightness variations under rotation. The cigar became the popular image because it was drawn early. Jackson and Desch's model actually implies the flattened pancake instead. That is a completely different object from the public imagination's version. We built a global argument about alien technology upon a brightness graph. Notice how closely that mirrors what happened 8 years later. Oumuamua was observable for a matter of weeks at most. It was discovered outbound, already past perihelion and already receding. By the time anyone understood the find, it had grown too faint. Then came August 30th, 2019, and a very different discovery. Gennady Borisov, an amateur astronomer in Crimea, found the second one. He used a telescope that he had built himself by hand. I want to give that detail its proper weight for a moment. The second interstellar object ever discovered came from a homemade instrument. It was found by someone working outside the professional survey system entirely. 2I Borisov proved almost reassuringly ordinary by comparison with its predecessor. It possessed a coma, and it possessed a proper tail. It behaved like a comet, for the straightforward reason that it was one. Its measured composition proved to be unusually rich in carbon monoxide. It later underwent a fragmentation event, shedding a visible piece. That happened in March 2020, and researchers watched it occur. A piece of another star system broke apart in real time. Crucially, it also showed the large dust grains we discussed earlier. Because Borisov was discovered inbound, months before its December perihelion, preparation was possible. Hubble observed it repeatedly across its entire passage through our system. Spectra were taken at many separate points along its trajectory. What Borisov taught us above everything else was reassuring at the time. Interstellar comets could be almost entirely ordinary in their behaviour. After Oumuamua's strangeness, that finding calmed the whole field considerably. The first object might have been an outlier rather than typical, and now 3I Atlas sits awkwardly between those two examples. It is clearly a comet, with clearly cometary activity throughout, yet its chemistry and polarization match nothing in our records. That list includes Borisov, which was supposedly the ordinary one. Now here is the number that ought to be far more famous. The Vera Rubin Observatory sits on a mountain in Chile. Its mirror measures 8.4 meters across the primary surface. Its camera contains 3.2 billion pixels of imaging capability. That is the largest digital camera ever constructed for astronomy anywhere. It began issuing public alerts in February of this year. On its first night of alerts, it produced 800,000 of them. Its full 10-year survey officially began on June 30th, 2026. That start date falls less than 1 month before tonight. Rubin should catalogue roughly 6 million solar system objects over 10 years. During commissioning alone, it logged around 11,000 new asteroids. Asked how many interstellar objects it should find, the observatory answered directly. Best estimates suggest between 5 and 50 across the 10-year survey. That wide range reflects how limited our population constraints remain. Earlier modelling work suggested perhaps 1 or 2 objects per year. Other models allowed for a range reaching 70 per year. Let me translate all those figures into something rather more meaningful. Objects from other star systems are not rare visitors at all. They have been passing through this system continuously for its entire history. They passed through during the age of the dinosaurs unobserved. They passed through the ice ages and all of recorded human history. We did not discover a rare event back in 2017. We discovered a blind spot that had always been there. And Rubin is about to remove that blind spot entirely, which means we are about to be handed several more of these. Every single one will arrive with the identical fundamental problem. They come in fast, they are detected late, and they leave within months. Darrell Seligman called Rubin the beginning of an entirely new era. He described it as revolutionizing the whole of time domain planetary science. He is right about the detection capability in every respect. But an era of detection differs from an era of investigation. Seeing something and reaching it are separated by that delta V figure. And that figure has not moved by a single kilometre per second. We are becoming extremely good at watching things we cannot catch. So the obvious question becomes what, if anything, is being built about it. Part 16. The spacecraft that should have been parked at Mars. 3 projects currently under construction change parts of this equation. It is worth understanding precisely what each one of them does. it matters even more to understand what each one does not do. The first is the Vera-Rubin Observatory, which we discussed already. Rubin solves the detection problem more thoroughly than anything before it. It will find these objects at rates we have never experienced, between 5 and 50 over 10 years by the observatory's own estimate. But detection is only half the problem, and probably the easier half. Rubin will hand us targets without handing us any way to reach them, and there is a subtlety making even that improvement less dramatic than expected. Rubin recorded 3i Atlas in verification data on June 21st. That was 10 days before Atlas formally discovered the object. 10 days is a genuine gain, and it is not 10 months. These objects arrive fast, from directions nobody happens to be watching. The fundamental limit is not telescope sensitivity or mirror diameter. You cannot see something before sunlight reaches it at sufficient intensity. Physics sets that boundary, and no instrument moves it very far. The second project genuinely represents new thinking about the problem. The European Space Agency's Comet interceptor is scheduled for launch around 2029. It will share a ride with the Aerial Telescope mission. Its concept differs from nearly every planetary mission ever flown. Rather than launching toward a known target, it launches toward a waiting position. It will travel to the second Lagrange point beyond Earth. That location sits about 1.5 million kilometres away. There it will park itself and wait, dormant, for years if necessary. When a suitable target appears, the spacecraft wakes up and departs. Suitable means a pristine long-period comet falling inward for the first time. With much lower probability, it could mean an interstellar object. The spacecraft is actually 3 separate vehicles flying together as one. A main vehicle carries 2 smaller probes toward the encounter. The Japanese Space Agency provides one of those 2 probes. They separate before arrival to observe from 3 different positions. Flyby distance is planned at roughly 1,000 kilometres from the target. Relative velocities could run anywhere from 10 to 70 kilometres per second. Colin Snodgrass and Geraint Jones lead the mission science team. I want to credit the agency for being honest about the limits. Their own material states clearly that catching something like this is unlikely. The mission's value lies in demonstrating rapid response from a waiting position. It is described as a pathfinder for possible future intercept missions. Read those words carefully, because they are doing important work. Pathfinder and demonstration are not remotely the same as solution. Could Comet Interceptor have caught 3i Atlas if it existed? It could not, and the reason is worth stating plainly. It has not launched, and it will not launch until 2029. Even sitting fueled at that waiting point in 2025, it fails. The required delta V from Earth's vicinity was 24 and climbing. Waiting at a Lagrange point does not solve that arithmetic. It shortens your reaction time, which is genuinely valuable in itself. Remember the paper and the brick. One final time tonight. You cannot catch the brick by throwing the paper harder. The third project is NASA's NEO-Surveyor Infrared Space Telescope. Amy Mainzer at UCLA leads the science team for that mission. It is currently targeted for launch no earlier than September 2027. Its purpose is finding near-Earth asteroids rather than interstellar objects. The stated goal is finding 90% of objects above 140 meters. NEO-Surveyor was never designed for objects like 3i Atlas, but it matters to this story for one specific reason. It observes in infrared, detecting heat rather than reflected sunlight. That capability lets it find dark objects that reflect almost nothing. It also finds objects approaching from directions where reflected light fails. The European Space Agency is separately developing a concept called Neomir. That spacecraft would sit at the first Lagrange point instead. It would station itself between the Earth and the Sun. Its job would be watching for objects arriving out of solar glare. That direction is where we remain functionally blind at present. It is precisely the direction the Chelyabinsk object arrived from in 2013. That gap is the single largest hole in our current coverage. Closing it needs an instrument that nobody has yet funded to completion. So combining all three projects gives a fair picture of our position. We are building substantially better eyes for finding these objects. We are building one modest, honest experiment in rapid response. We are building nothing capable of catching something at 58 kilometres per second. That is not a criticism of the agencies involved in any way. The delta V problem is not primarily a funding problem. It is a propulsion problem, and propulsion resists money in ways funding cannot fix. Chemical rockets sit close to their theoretical performance limits already. Nuclear thermal, nuclear electric, and solar sail concepts all need decades of development. None of them could have been assembled inside 120 days, which leaves the one option that actually worked on paper. Not chasing from Earth, but launching from somewhere better positioned. 5 kilometres per second from Mars, rather than 24 from here. We are going to have infrastructure at Mars across the coming decade. Multiple agencies plan sample return missions and human precursor flights. Orbital relay networks are being designed for that environment already. And the single most useful lesson from this entire episode is straightforward. A small, cheap, fueled spacecraft parked in Mars orbit would have been priceless. It would have been worth more in August 2025 than almost anything else. Not because Mars itself is scientifically important to this question, because Mars is somewhere else, and somewhere else is the entire point. Having assets distributed across multiple locations means geometry cannot trap you completely. When one position deals a bad hand, another position holds cards. We had a dozen spacecraft at Mars watching this object helplessly. We did not have a single one that could actually move. Let me describe what the alternative would genuinely require, because it is unexotic. You would not need a flagship mission or a nuclear engine. You would not need a decade of dedicated technology development either. The mathematics called for a spacecraft of perhaps a few hundred kilograms. It would carry a chemical stage delivering 5 to 7 kilometers per second. It would need a camera, a dust detector, and a mass spectrometer. Every one of those components has flown successfully many times before. The propulsion is ordinary, and the instruments are entirely conventional. Hibernation and waking it later is already proven. The same logic applies at Mars, with one crucial advantage. Mars is somewhere genuinely different rather than somewhere merely adjacent. The cost would be genuinely modest within existing planetary science budgets. The shelved Diana spacecraft was small, already built, and cancelled separately. Their cancellation had nothing whatsoever to do with any of this. So the hard part is not engineering, and it never was. The hard part is institutional, and the difficulty is worth naming. You would be asking an agency to fund a spacecraft with no target. It would have no schedule, no guaranteed science return, and no defined mission. It might sit at Mars for 15 years and never fire its engine. There exists no good mechanism anywhere for funding that proposition. Every review process ever designed asks what a mission will accomplish and when. A standing readiness asset cannot answer either of those questions honestly. Its entire value lies in being available on an unpredictable day. That is precisely why no such thing exists at Mars tonight. Nobody involved was foolish, and nobody made an obviously wrong decision. Our institutions are built to fund known objectives with defined outcomes. What this particular situation required was something much closer to insurance. Insurance always looks like waste, until the moment it looks like foresight. Those 4 months in 2025 were the moment it would have looked like foresight. And the next such moment is already somewhere on the calendar. Part 17. The clock that is still running tonight. 2 processes are running simultaneously, and they move in opposite directions. Understanding both is the only way to understand where this ends. The first process is the data still arriving from that encounter. Follow that whole sequence carefully across the past 12 months. The object passed close by Mars in early October 2025. The Tianwen-1 images from that encounter appeared as a preprint in March. Formal publication followed on May 14th of this year, 2026. The general public encountered the findings only in the past several days. That is roughly 10 months between photons striking a detector and public awareness. JUICE observed at perihelion and could not transmit until February. The isotope results reached publication in June of this year. NASA's Juno spacecraft was near Jupiter during the March encounter. More than 4 months later, no Juno observations have been released. Loeb himself was writing in late April that everyone was still waiting. We are still waiting tonight, and that data may never arrive. The second clock is the object itself, departing from us permanently. 3I Atlas sits in the constellation Gemini at magnitude 15 or fainter. It is roughly 1 billion kilometres away and receding steadily. It is well beyond Jupiter now, and it is not slowing. It cannot slow down, because its orbit is mathematically open. No force in this solar system can bend that path closed. Every day it grows fainter, and every week fewer instruments can find it. A point is coming when the last telescope loses it entirely. Now place those two clocks side by side and watch. The data arrives on a timescale of months and years. The object departs on a timescale of months as well. The object is winning that race, and it always was. In normal science, a surprising result invites verification from somebody else. You take another measurement, or you point a different instrument. A colleague then attempts to reproduce your finding entirely independently. That process of return and verification is the foundation of knowledge. That option no longer exists for anything measured about this object. The polarization anomaly, deeper than any ever recorded, remains unexplained. Nobody can go back and measure it a second time. The nucleus size, uncertain by a factor exceeding 10, stays unresolved. The carbon dioxide ratio cannot be checked at another point in its activity. There is no more activity, and there will be no more data. Whatever sits in Juno's memory is the last information this object generates. Let me return to where all of this started tonight. There were 57 photographs, taken by a camera 16 inches across. It sat aboard a spacecraft built for a completely different job. Engineers slewed it off target and operated it beyond its design limits. They stacked 30-second exposures of a grey smudge 29 million kilometres away. That was humanity's best look at a 12 billion-year-old object. Not a mission, not a rendezvous, and not a sample. An improvisation assembled in 3 weeks by people who refused to waste the chance. And the genuinely remarkable thing is that the improvisation worked. Those frames gave us the grain sizes with real precision. From grain sizes came ejection velocities and the mass loss rate. From those came a constraint on where in another system it formed. Coarse sand rather than smoke. From the frozen edge of a vanished disk. That is real knowledge about another planetary system, pulled from a blur. So the failure was never in the observing, which was extraordinary. We proved we can observe when something unexpected arrives without warning. 2 planets worth of spacecraft turned toward one faint moving dot. What we did not prove is that we can respond. Observation and response are different problems with entirely different solutions. We have spent decades becoming excellent at the first one. We have spent almost no time at all on the second. 3I Atlas will keep going, indifferent to all of this. It will cross the orbit of Neptune sometime in the 2030s. It will spend hundreds of thousands of years crossing the dark between stars. Eventually it will pass through some other star system entirely. If anything there is watching, they will see a small dark object. It will be moving at 58 kilometers per second, carrying ancient chemistry. Nothing about it will be different for having passed through here. So the question I asked at the start remains exactly where it started. Did we learn what 3I Atlas was, or only how unprepared we were. I am not going to resolve that tonight, because it is not resolved. The polarization stays unexplained, and the nucleus was never measured. The Juno data has not been released to anyone at all. Every one of those gaps became permanent the moment the object receded. Somewhere out past Jupiter, that grey smudge is still moving away from us. And Rubin has been surveying for less than a month.